Bridging the divide. Uniting relativity and quantum mechanics in the quest to understand the universe. In the ongoing journey to answer the most profound questions in cosmology, such as what the universe is made of, how it began, and what its ultimate fate may be, researchers are increasingly focused on developing a unified hypothesis. This new theoretical framework must harmonize two of the most groundbreaking ideas in modern physical science: Einstein's theory of general relativity and the quantum hypothesis. Einstein's general theory of relativity, published in 1915, revolutionized our understanding of gravity by describing it not as a force, but as the curvature of space and time caused by mass and energy. This theory has since become the cornerstone of what we know as classical cosmology. One of its most powerful implications is the concept of the Big Bang, the idea that the universe had a beginning, an initial singularity from which all matter, energy, and even spacetime itself emerged in an enormous explosion roughly 13.8 billion years ago. According to this view, the cosmos has been expanding and evolving ever since. On the other hand, the quantum hypothesis, developed in the early 20th century by pioneers like Max Planck, Niels Bohr, and Werner Heisenberg, deals with the universe at the smallest scales. It reveals a world that is unpredictable, probabilistic, and governed by the strange behavior of particles and waves. Quantum mechanics has been incredibly successful in explaining the behavior of atoms, photons, and subatomic particles, and it underlies much of the modern technology we rely on today. Despite their individual successes, these two foundational theories are fundamentally incompatible. General relativity describes the large-scale structure of the universe, galaxies, black holes, and cosmic expansion, while quantum mechanics rules the microscopic realm. However, in extreme environments, such as the centers of black holes or the moment of the Big Bang itself, both theories must apply simultaneously. This presents a major problem. The mathematics of general relativity and quantum mechanics do not align. Attempts to combine them often lead to infinities and contradictions. This has led scientists to search for a deeper, more unified theory, one that can seamlessly integrate the smooth fabric of spacetime with the jittery, probabilistic nature of quantum fields. One promising approach is string theory, which proposes that the fundamental constituents of the universe are not particles, but tiny, vibrating strings of energy. Another is loop quantum gravity, which seeks to quantize space and time themselves. These, and other efforts, are part of a larger goal: to construct a theory of quantum gravity that can explain all physical phenomena, from the birth of the universe to its large-scale structure and evolution. Recent advancements in observational cosmology, such as data from the James Webb Space Telescope and gravitational wave detectors like LIGO, are also providing fresh clues. These instruments are capable of probing the early universe and extreme cosmic events with unprecedented precision, offering new ways to test theories and refine our understanding of the cosmos. In conclusion, to unlock the deepest mysteries of the universe, researchers must do more than build on existing ideas, they must unite them. By bridging the gap between general relativity and quantum mechanics, scientists hope to uncover a single, elegant framework that explains where the universe came from, what it is made of, and perhaps even why it exists at all. Pushing the boundaries, the road ahead for a unified theory of the universe. As the pursuit of a unified theory continues, collaboration between theoretical physicists, astronomers, and experimental scientists becomes increasingly critical. No longer confined to blackboards and abstract equations, the quest now draws heavily from real-world observations, turning the universe itself into a vast, dynamic laboratory. One of the most exciting frontiers lies in the study of black holes. These mysterious regions of space, where gravity is so intense that not even light can escape, offer a unique testing ground for both general relativity and quantum mechanics. The recent success of the Event Horizon Telescope in capturing the first image of a black hole shadow in 2019 has opened the door to even more precise measurements of these cosmic giants. Such data could help validate or challenge existing theories and point toward new physics. At the other end of the cosmic timeline, scientists are also exploring the earliest moments after the Big Bang, specifically, the period known as cosmic inflation. This rapid expansion, thought to have occurred within fractions of a second after the universe's birth, holds clues about the fundamental forces that shape the cosmos. Experiments such as the Cosmic Microwave Background Observations, CMB, aim to detect subtle patterns in ancient radiation that could confirm or refute inflationary models. These efforts may also provide indirect evidence for the quantum fluctuations that seeded the structure of galaxies. Meanwhile, quantum experiments on Earth are growing increasingly sophisticated. Particle accelerators like the Large Hadron Collider continue to search for new particles and interactions beyond the standard model. The detection of phenomena such as supersymmetry, dark matter particles, or extra dimensions could radically shift our understanding and bring us closer to a theory that unites quantum mechanics with gravity. Another important piece of the puzzle is dark energy, the mysterious force driving the accelerated expansion of the universe. Though we know it makes up nearly 70% of the cosmos, its nature remains unknown. Unlocking its secrets may require a quantum understanding of space itself or entirely new theoretical frameworks that transcend current models. Crucially, the next generation of scientists is being trained not to think in silos, but to work across disciplines. From computational physics to cosmological simulations, and from quantum field theory to experimental astrophysics, the future of cosmology lies in integration. With artificial intelligence accelerating data analysis and modeling, we may be on the cusp of breakthroughs once thought impossible. While we have not yet found the final equation that explains everything, every discovery, whether confirming or disproving a theory, brings us one step closer. The quest for a unified theory is not just a scientific endeavor, it is a reflection of humanity's deepest desire to understand our place in the cosmos. As we peer deeper into the universe and uncover its secrets, we are, in essence, learning the story of ourselves. Unraveling the cosmos, the story of the universe's origins and fate. The exploration of the universe's origins and structure stands as one of the most profound and challenging pursuits in modern science. For centuries, humanity has gazed at the stars, seeking to understand not only where we come from, but where we are headed. This cosmic journey has taken remarkable turns, especially with the discovery of a mysterious force that defies the intuitive pull of gravity, dark energy. Before dark energy was revealed in the late 1990s, scientists held a relatively straightforward view of the universe's future. It was generally believed that, after the Big Bang, the universe's expansion, initially rapid, would gradually decelerate under the influence of gravity. The collective mass of galaxies, stars, and dark matter was thought to be enough to either slow the expansion to a crawl or eventually reverse it, potentially leading to a big crunch, where the universe would collapse back into a dense point. However, observations of distant supernovae and cosmic background radiation painted a very different picture. Instead of slowing down, the expansion of the universe was accelerating. This unexpected finding pointed to the existence of dark energy, an invisible and poorly understood force that appears to counteract gravity on the largest scales. Dark energy makes up about 68% of the universe, yet its nature remains one of the biggest unsolved mysteries in physics. If the influence of dark energy continues unchecked, the fate of the universe could be dramatically different from previous predictions. Over trillions of years, galaxies would drift farther and farther apart. Stars would burn out, and the cosmos would become a cold, dark, and isolated expanse. This scenario is known as the Big Freeze or heat death, a state where the universe reaches maximum entropy, with no usable energy left to sustain processes like life or star formation. In this frozen future, the universe would continue to expand forever, becoming increasingly empty and quiet. Black holes would eventually evaporate through Hawking radiation, and even subatomic particles might decay. While this outcome seems distant and bleak, it underscores the importance of understanding dark energy and the underlying laws of the cosmos. The study of the universe's beginnings and structure not only helps us predict its future, but also sheds light on the fundamental forces and particles that shape reality. Through instruments like the James Webb Space Telescope and experiments at particle accelerators, scientists continue to probe the earliest moments of the cosmos, striving to answer the ultimate questions: how did everything begin? What is the universe made of? And what will become of it all? As our understanding deepens, one thing remains clear: the universe holds more mysteries than we can yet imagine, and the quest to unravel them is far from over. Humanity's role in the cosmic story. Despite the vastness of the universe, we, as humans, have developed the remarkable ability to observe, question, and theorize about the cosmos from our tiny corner of space. Through curiosity, innovation, and relentless inquiry, we've built sophisticated tools, from ground-based observatories to space telescopes, that allow us to look billions of years into the past. Every photon of light captured from distant galaxies adds a new piece to the cosmic puzzle. Theoretical models and simulations, powered by advanced computing, help scientists understand how the early universe evolved into the complex structure we see today. From the formation of the first stars to the web-like distribution of galaxies across space, each discovery gives us a glimpse into the forces at play during the universe's formative years. In parallel, particle physics experiments, such as those conducted at CERN's Large Hadron Collider, probe the smallest building blocks of matter. These experiments aim to uncover how particles acquire mass, how fundamental forces interact, and whether unknown particles might be responsible for phenomena like dark matter and dark energy. The philosophical frontier. Beyond scientific exploration, the study of the universe raises profound philosophical questions. If the universe is destined for a cold, dark end, what does that mean for the meaning of life, consciousness, or the value of our brief moment in cosmic time? Some see this knowledge as a humbling reminder of our fragility. Others view it as an inspiration to cherish our existence, to seek understanding, and to create meaning while we can. Moreover, the realization that the universe had a beginning leads to age-old questions once confined to theology or philosophy. What, if anything, preceded the Big Bang? Is our universe one among many in a multiverse? Can something come from nothing? These questions remain largely speculative, but they highlight the boundary where science meets the limits of human imagination. Looking ahead. As we continue to study the universe, new technologies and missions promise even greater discoveries. Future telescopes will allow us to peer deeper into space and time, possibly observing the first moments after the Big Bang or detecting biosignatures on distant exoplanets. Missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid will specifically target dark energy, aiming to better understand its nature and behavior. At the same time, collaborations across disciplines, astronomy, physics, mathematics, computer science, and philosophy, are helping to build a more holistic picture of the cosmos.